Okay, we're going to go ahead here. I hadn't noticed, which I forgot now. Just a reminder, at the banquet tonight, there will be a First Nations dance demonstration or performance. So you don't want to miss that, I guess. Okay, we're going to get going. The organizers chose as the theme for the Canadian Symposium Catalysis of 19. The theme was bridging between, or building bridges between academia and industry. And something I guess we haven't done at the symposium before. We decided to have an industry panel, or at least a panel discussion. And what we have done, we've assembled 6 experts here who can give us different perspectives on that theme of building bridges. We're also talking, I guess, about the innovation chain between research and commercial production somewhere. But really, it's all about building bridges between academia and the industry. And as I said, in the handouts, there is a brief biography of each of the 6 panel members. What I'm going to do right now is just introduce the 6 of them in a row and invite you to read their biographies. They are in the overheads. And then we'll go one at a time. So the procedure is we're going to have each of them give a 10-minute presentation. There'll be time at the end for some questions. A couple of points. If you get the chance, write down your questions on a piece of paper. I'm hoping that there will be a few questions at the end. But if you don't get your questions answered, please write it down, give it back to me, or give it to Alan Nelson. What we'd like to do is compile a description at the end of the proceedings here. Okay, so first of all, I'm going to introduce the speakers, and then we're going to go through 10-minute presentations. It's an hour long, and we're going to try to be as fast as possible. So bear with us and save your questions till the end. Okay. To introduce the panel, first of all, from your left to right, Paul Clark, Vice President R&D, Nova Chemicals. Leo Manzer, President, Catalytic Insights. John Adjay, Leader, Hydroprocessing Catalyst Development, Syncrude Canada. Sai Katakanani, Director of EFC Process Technology, Geosalt Energy. Bryce McGarvey, from the Research Department of Imperial Oil. And Mike White, Director, Institute for Interfacial Catalysis at Pacific Northwest, and also still a professor at the University of Texas at Austin. So we're going to go through 10-minute presentations, and first Paul White from NOVA. Paul.
Thanks, Craig. I'll try to honor the guidelines. That's prepared notes here to keep it within the 10-minute guidelines that Craig has just finally enforced here. So it's a pleasure to be with you this afternoon and lead off this industry session on building catalytic bridges between academia and industry. This is a topic that's near and dear to my heart, as I've seen great benefits from building such bridges. The picture on my opening slide is an appropriate one. It shows the Blue Water Bridge connecting Sarnia, known as Canada's Chemical Valley, to the United States. Now, the first bridge was built in the 1930s and was such a success that the second span was erected in the 1990s. So let's explore the power of building industry university bridges in catalysis. Next slide. But first, a quick profile of my company, Nova Chemicals. For those of you not familiar with us, we are a medium-sized chemical polymers company on the world stage, but have a significant North American presence as the production numbers show on this overhead. Our main Canadian manufacturing sites are in Sarnia, Ontario, and Joffre, Alberta, just outside Red Deer. And to give you an idea of our size, the Joffre site is the largest single site for the manufacture of ethylene, a key monomer of our industry. It's the largest site in the world, at about 6 billion pounds a year. On the technology front, we are also a significant player in Canada. Our major research and technical application centers are located in Calgary. Spend on technology at about $65 million. That places us 33rd in Canada's top 100, and we're second in spend in the province of Alberta. Our research technology, commercialization efforts have garnered us a number of awards. And one final note, in spite of the commodity nature of our chemicals and polymers, our industry is technologically intensive, particularly in advanced areas such as modeling, simulation, advanced process control, material science, and most importantly for this conference, catalysis. Next slide, please. So let's further explore the role of catalysis in this technologically intensive polymers industry. Catalysts have many roles to play in our industry, but I will restrict my talk this afternoon to development and use of catalysis and polymerization. These catalysts, primarily based on active metals in the 4 and 5B groups on the periodic table, are extremely productive, yielding tons of product, final polymer per pounds of catalyst consumed, so you get an idea of the activity. And due to this high activity, these catalysts are generally classified as pyrophoric and have to be handled with extreme care and caution within the laboratory and within our industry setting. To understand the power of catalysis in our industry, one should examine the original process for the manufacture of polyethylene, a major commodity polymer. And the first polyethylene was produced in 1939 by ICI in England, using extremes of pressure and temperature. To give you a feel, 50,000 pounds of reactor pressure requires triple powerful compressors and reactors with 2-inch thick steel walls, not your average process. The breakthrough using catalysis occurred in the 1950s with the inventions of Drs. Ziegler and Natta. Their catalyst species employed the active metals I mentioned earlier, and the result was significant reduction in reactor operating conditions, rapid commercialization to a current commanding position in the manufacture of polyethylene and polypropylene. And today we're benefiting from further advancements in catalysis with even higher efficiencies in producing product in combination with other process improvements. And certainly we're seeing ongoing debottlenecking of manufacturing capacity using non-capital intensive approaches. Next slide, please. Our previous discussion on the latter slide is focused on the process or production aspects of polymerization catalysts, but there's a second equally important feature of these catalysts, that is their ability to control and shape the performance of final polymers themselves. These polymers, such as polyethylene and polypropylene, find their way into a variety of applications familiar to us in our daily lives: food wrapping, pipe, high-performance sports goods, a myriad of application areas. Now, from the polymer itself, which we manufacture in pellet form, there is a final conversion process involving heated extrusion, molding, and forming. And performance in this area is measured in 3 ways. First, processability through the customer's fabrication equipment. Then optical properties such as clarity, and finally strength properties. And the desire, of course, is to have all 3. Now, with the original ICI process, this process yielded polymers that had exceptional processability and optical properties, but lacked the strength properties, and hence early uses of these polymers were quite limited. First use, in fact, was wire coating, which was used to help the war effort in aircraft to prevent the corrosion of various wires and the like within aircraft. Now, the second generation of catalyst breakthrough came with the Ziegler-Natta catalyst, and this opened up whole new fields of polymer performance as well as production. The one catch, though, is that the Ziegler-Natta-based catalysts lack in processability compared to the earlier process. And then the final generation, I guess I'm calling that the second generation of catalysis, is yielding products that have not only the processability aspects of the resin, but also the desired physical properties, strength, clarity, and the like. Now, as you can see, catalysis has brought huge benefits to the polymers industry and a strong competitive field to develop new versions of these catalysts. Next slide, please. Given the obvious value of catalysis advancement, I'd like to set the stage for the growing importance of creating research bridges between university and industry. The first truism is that the traditional pathway of company self-development has become prohibitively expensive, as exemplified by the staggering investment numbers shown on this board. Not only is the road costly, but the fruits of labor have diminished over time. Thus, the emphasis for industry development of catalysis has shifted to the universities as a source for new discoveries. This new wave has benefited companies like Nova Chemicals by leveling the playing field of large players versus small players or medium-sized players. And on this basis, we've created a strategy of astute acquisition of catalyst technology, which I'll describe on the next slide. So we have formed a strategy of acquisition based on collaboration with universities. And our first task was and is to properly define our needs in catalysis technology. And here we took a visionary approach to fully define our future needs We then framed these needs in descriptive terms usable by university and translatable by university academics. The challenge here is to strike the right balance between being too restrictive, thus stifling creativity, or too broad and vague. We have spent considerable effort on refining these descriptors and view this as an enriching exercise for our scientists and research engineers. Next, we set about to profile the capabilities of universities in our area of catalyst interest. Our first focus is on Canadian universities based on both the strength of these institutions and the ease with which I call active collaboration between ourselves and the universities. Our strategy is also harnessed what I call the full power of leveraging. Here again, Canada forms ideal grounds. We utilize the full array of avenues from creating research chairs to joint project funding with a battery of agencies to the use of the SR&ED tax credits, where we as a company typically garner about $8 to $10 million a year of these credits. One bit of wisdom gained in our quest for university collaboration is to cast your net widely. Some of our best discoveries have come from lesser-known universities. As I say, all it takes is one researcher with a novel idea, and we all know what happens. Next slide, please. Let me briefly share a success story with you. Our challenge in the mid-1990s was to develop our own proprietary single-site metallocene-like catalyst position in a hotly contested field heavy with patents. Investment had been huge, and remember that earlier $5 billion number. Our approach to this daunting task was to develop the strategy I've already described and move into action. As mentioned, we reserved some of our time and effort for the lesser-known universities in this field of interest. Next slide. The outcome of our endeavors has more than exceeded our expectations. We found a fit with unique catalyst species based on phosphinamines developed by Dr. Douglas Steffen at the University of Windsor. A program of intense collaboration was quickly developed, and we leveraged our activity to the hilt. The result was the creation of the Emerald family, that's our brand name, a proprietary single-site catalyst, which we collaboratively scaled up in a very short time. And today, these catalysts are successfully employed in our new state-of-the-art 850 million pound a year manufacturing plant in Alberta. The process runs exceptionally well with these Emerald catalysts, but it's the properties of the resins that are truly outstanding. We are producing high-value products that nobody else can make, and we believe that we've attained a position of parity with the industry leaders in technology in this area at roughly 1/10 the invested cost, which is quite a remarkable achievement. Our joint efforts culminated with the University of Windsor and Nova Chemicals winning the Insert Synergy Award in 2003. I'm also proud to say that our Dr. Stephen Brown, winner of this year's CIC Catalyst Award, has been a major contributor to our success. You'll hear more about this tomorrow, I'm sure, in his awards lecture. Next slide. Here's a quick look at what 850 million pounds of capacity looks like employing our Emerald catalyst. This is the world's largest solution train for the manufacture of polyethylene. Next slide, please. So what are some of the unmet needs in catalysis that our vision and strategy have identified? We always try to inspire, so I've included the Olympic motto, which may translate into the language of technology as tougher, stronger, clearer, more active, on and on. On the process side, we're seeking catalyst robustness, lower cost of manufacture, because these catalysts can be very expensive species to manufacture on a large-scale basis. And we're also looking at ease of manufacture control of the total polymerization process using advanced process control. Next slide. As for product needs, among many, we are seeking improved comonomer incorporation. These products not necessarily are made solely from ethylene as a starting material. We also incorporate other comonomers like butene, hexene, and octene. So we're looking at more effective comonomer incorporation. Control of polymer architecture is an elegant way of saying the ability to control structure and feature of polymer to match customer needs, and we have an excellent handle on that. And then finally, because these catalysts are not removed from the process, they have to be low residual in a leave-in basis. And remember that these are the high-cut excerpts from our more comprehensive needs list, which we freely share with interested universities. Final slide. Now, to conclude, catalysis advancements have created welcome paradigm shifts in the polymers industry, and I'm sure these are going to continue. Nova Chemical's strategy for technology acquisition has benefited strongly from university discovery research and powerful collaboration between the two parties. And in the process, Nova Chemicals has transformed itself into being among the industry leaders. The building of collaborative catalytic bridges, as symbolized in the arch of the rainbow over our Joffre site and this picture here, have been essential to our success. Thank you, and I look forward to your questions later.